Okay, so we'll see some parameters which will play an important role in three-phase induction motor. Like first one is slip. So we know that the magnetic field is rotating whenever three-phase supply is given to the stator winding. It produces rotating magnetic field and whose speed is denoted by ns, n suffix s, that is called synchronous speed, right? Whose formula we have derived, which is 120 f by p. So this is what the speed at which the magnetic field rotates, where f is the frequency of supply and p with the number of poles. For example, if frequency 50 Hz and number of poles are 4, then synchronous speed will be 1500 RPM. So in this way, we can calculate the speed at which the magnetic field rotates. And there is another speed called rotor speed. This is the speed at which rotor rotates. So the synchronous speed at which magnetic field rotates, denoted by ns, and the speed at which rotor rotates, it is called rotor speed and denoted by capital N. So see the difference, ns and n. These are two different speeds. Now, when the rotor accelerates in the direction of rotating magnetic field, but it can never achieve the speed of stator flux. Why it can never achieve? Because when the rotor rotates in the same speed as that of the rotating magnetic field, there will be no relative motion. ns is equal to n, therefore the slip will be 0. So at that time there will be no relative motion and the induced EMF in rotor conductors will be 0. As the rotor conductor induced EMF is 0, there will be no current, no torque developed, and the rotor speed slows down. As the rotor speed slows down, there will be again induced EMF in the rotor conductor due to relative motion, and hence again there will be a torque, there will be acceleration of rotor. So this process continues, but we conclude that the rotor can never achieve the speed of stator flux, right? So this is what written in these points. Okay, so whenever there will be a difference between the rotor speed and stator field, this difference is known as the slip speed, right? And which is usually expressed as a percentage of synchronous speed. So this is called percentage slip. Got this? What is slip? The difference between the synchronous speed ns and the actual speed of rotor n, which is called slip. And when we want to express in terms of percentage, then this can be expressed by this form. Percentage slip S is equal to ns minus n divided by ns multiplied by 100. So by this formula, we can calculate the percentage slip. And the fractional slip, we simply S is equal to ns minus n by ns. So this is the fractional slip. So we'll get some points, some observation by this formula. The quantity ns minus n is sometimes called slip, right? Ns minus n, the difference between synchronous speed and actual rotor speed, which is called slip speed. But when the rotor is stationary, that is the speed is 0, then slip will be 1 or 100%. You can observe another thing is that whenever the speed is 0, then n is equal to 0, put here. So S is equal to ns by ns. So it will be 1. So slip will be 1 or 100%. So this is the maximum value of slip. In an induction motor, the change in slip from no load to full load is hardly in between 0.1% to 3%. So it is essentially called a constant speed motor. The value of slip is not more than 3%. That is in terms of 0.03. Fractional value will be 0.03. So that's why this motor is almost a constant speed motor, like DC shunt motor. DC shunt motor, in that case also the flux is constant, hence that motor also called constant speed motor. Similarly for three-phase induction motor. So this is called slip in three-phase induction motor, and whose formula you have to remember, ns minus n by ns multiplied by 100. So this formula you have to remember. Second parameter, which is a rotor current frequency. Now we know that the stator current frequency, which is nothing but the supply frequency, as we know in India, three-phase supply is denoted by RYB, red, yellow, blue. Their voltage is 440 volt for distribution level, and the frequency is 50 Hertz. Right? So this is the standard supply for three-phase, and there we have derived the formula for synchronous speed. Ns is equal to 120 F by P. So this is similar for the rotor speed. So if we rearrange, then the frequency which is equal to Np by 120, rearrange केला था formula ला. So frequency is equal to Np by 120, where N is the relative speed between magnetic field and rotor, and P with the number of poles. Here consider N is the relative speed between magnetic field and rotor. Now for rotor speed N, the relative speed between the rotating flux and the rotor is ns minus n. So in previous topic we have seen that the slip speed, that is nothing but ns minus n. So this is nothing but the relative speed between rotating flux and the rotor. हा difference म्हणजेच काय relative speed आहे ना, येतं लक्षात. ns minus n, this is nothing but the relative speed, the difference between both speed. So consequently the rotor current frequency f dash is given by, now we will denote rotor current frequency by f dash. So that is equal to ns minus n. So this n, we assume that this is the relative speed. So relative speed is nothing but ns minus n. So we can put it here. F dash is equal to ns minus n P by 120. Again, we have the formula for slip. S is equal to ns minus n by ns. So if we rearrange this formula, so we will get this type of formula. So ns minus n, take this ns to the right side. Here we will write in the left right side s into ns. So ns minus n, which is equal to s into this ns. So this is what we can put here. So ns minus n is equal to s into ns, and here number of poles as it is, divided by 120. Again we have the frequency f is equal to ns p by 120, right? So we can put there substitute f. So the resultant will be s into f. So f dash is equal to simply slip times the stator supply frequency. So this is what the rotor current frequency, which is equal to the fractional slip multiplied by supply frequency. So we can simply calculate the rotor current frequency. This is what was running. This is not at standstill. Stationary position ला जेव्हा rotor असेल तेव्हा हा फॉर्म्युला ऍप्लिकेबल नसतो. At that time, the rotor frequency is equal to stator frequency. Look at the 2 points we can observe. So remember this formula. The rotor current frequency while running is equal to the fractional slip multiplied by supply frequency. Two observation from above equation. The first one is when the rotor is at standstill or stationary, that means slip is equal to 1, n is equal to 0, so slip will be equal to 1. The frequency of rotor current is same as the frequency of supply current. So that's what I said. F is equal to 1, so F dash is equal to F. That means the stator frequency is equal to rotor frequency. Whenever the rotor is at stationary, म्हणजे जेव्हा आपण सप्लाय देऊ तेव्हा रोटर स्टेशनरी असेल त्या कंडिशनला दोन्ही फ्रिक्वेन्सी इक्वल असते. And second point, as the rotor picks up speed, the relative speed between the rotating flux and rotor decreases. Consequently, slip and the rotor current frequency also decreases. Right? So motor takes up speed, then this relative speed will decrease, and the resultant slip and the rotor current frequency also decreases. So this is, we can simply calculate by this formula. So this is second parameter, rotor current frequency. Then now similarly we can write the relation for rotor induced EMF per phase, rotor reactance per phase, and the frequency we already noted it. Look at, when the rotor is stationary, AC equal to 1. So under this condition, the per phase rotor EMF E2 has the frequency equal to that of the supply frequency F. So this is for the frequency for current and voltage, right? So as the frequencies are equal, then the induced EMF also equal, right? So because whatever the frequency changes, there will be a flux change. So at any slip S, the relative speed between the stator field and the rotor is decreases. Consequently, the induced EMF in the rotor and the frequency also reduced, which is proportional to S times E2 and S times F. At the same time, the per phase rotor reactance X2, which is also frequency dependent parameter, which also reduces to S times X2. So we generalize for any slip S, we can write the rotor induced EMF per phase, which is equal to S times E2, the rotor reactance per phase, which is equal to S times X2, and the rotor frequency, which will be S times F, where E2, X2 and F, which are the corresponding values at standstill. या सर्व values stationary साठी. E2, X2 and F, these are the values at standstill whenever the rotor is stationary. And whenever the rotor is running, then at that time we have to multiply by F. So remember this point. Running condition ला S ने multiply करायचं, slip ने multiply करायचं, आणि stationary position ला असेल तर जे स्टेटरचे पॅरामीटर्स आहेत तेच रोटरचे पॅरामीटर असतील. बिकॉज S इज इक्वल टू 1, स्लिपची व्हॅल्यू 1 असेल आणि n ची व्हॅल्यू 0 असेल. रोटर स्पीड विल बी 0. Then the last parameter, which is the rotor current. Now what will be the equation of rotor current and power factor, that we'll see in this equation. Now just consider a 3-phase induction motor and which is running into condition. At running condition, at running, consider slip S, and the rotor is assumed to be a wound type and star connected 3-phase stator winding as well as rotor winding. So this is star connected stator winding and star connected rotor winding. As we know, the star connection there will be a 3 pages. For every 3 page, 1 point is shorted, and another 3 terminals are brought out for connecting 3-page supply. Now, as there will be a winding, so it will have reactance and resistance. For every conductor, there will be a resistance. So mark it as R1 and X1. R1 and X1, these are the resistance and reactance for phase 1. So suppose say this is phase 1, phase 2 and phase 3, or we can say RYB. So R1 and X1, we have marked resistance and reactance, and the voltage across this page will be E1. So this is the stator winding. And for short circuited rotor winding, we'll mark R2 with the resistance and S times X2 with the reactance. As it is for running condition, so we can multiply by slip. But this, there will be no multiplication for resistance R2. Because why? The resistance is independent of frequency, hence we cannot multiply by S, which is a linear term. Resistance whose value doesn't depend on frequency, so which is always constant. Their value will be always constant, whatever the value of slip, whatever the value of frequency. So the resistance will be constant. We must not multiply by slip. And now, as this 3-page induction motor is balanced load nothing but the load across all 3 pages are equal, hence we can call it as a balanced load. म्हणजे तिन्ही फेजला इम्पेडन्स सेम असेल, बरोबर. मग तिन्ही फेजला जे काही करंट फ्लो होत आहे ते पण सेम असेल, right? So this type of load is called balanced load. If there will be an unequal impedance across 3 pages, then this is called unbalanced load. So as the motor represents a 3-page balanced load, so we need to consider only 1 page, and the condition in other 2 phases will be similar. So first of all, let's see at stationary condition. So consider 1 phase. So here we have, for rotor circuit, we have E2 is equal to the reactance X2 and the resistance R2, and the current flowing through will be I2. So rotor current per phase I2 is equal to E2 by Z2. This is simply Ohm's law. Ohm's law for DC circuit is V is equal to IR for DC circuit, and V is equal to I Z for AC circuit. Look at it. So instead of resistance, we consider impedance in case of AC circuits. So therefore, I is equal to what? V by Z. In case of AC circuit, I is equal to V by Z. So use here. I2 is equal to E2 by Z2. E2 का बर घेतला तर इथं voltage E2 ने denote केलेले आहे. So divide by Z2. Then E2, then we have to represent this impedance in terms of the combination of resistance and reactance, right? So impedance is nothing but the combination of resistance and reactance. So we can denote by under root of R square plus H square. We generally write this Z is equal to R plus minus J X. So we write in the rectangular representation. So again, with the help of the impedance triangle, we can denote. So this base term, base side represent the resistance. This adjacent side represent the reactance, and hypotenuse will represent the impedance, and this will be the angle phi. So this is the impedance triangle, by which also we can write the formula for impedance by Pythagoras. Z square is equal to R square plus X square. So Z is equal to under root of R square plus X square. or we can simply use rectangular to polar representation. So here we put Z2 is equal to under root of R2 square plus X2 square. Similarly, rotor power factor cos phi 2. Right? So in AC circuit, there will be a phasor diagram, there will be a waveform. So there will be some rectangular polar representation. That is called mathematical representation of the phasors. So cos phi 2 is equal to R2 by J2. This is again from this impedance triangle. So this is the angle phi between resistance and impedance. So cos phi is equal to adjacent side by hypotenuse. So cos phi 2 is equal to adjacent side is R2 and hypotenuse is Z2. These are the two suffix, right? So R2 by J2. So we have R2 as it is, and J2 is nothing but under root of R2 square plus X2 square. So this is at stationary position. We have not multiplied by slip. So while running, we need to consider the same phase, and we'll write the rotor current and power factor at running condition. So denote by I2 dash, so which is equal to S E2 by J2 dash. So SE2 as it is, and here on the numerator denominator R2 square plus X X2 brackets. So similarly for rotor power factor. So simply multiply by S to the reactance. So got this? So these are the rotor current and rotor power factor while the motor is running and also at standstill. So hope you understood these parameters, so which will be very helpful in understanding some expressions, torque equations, like other expressions also, like power stages. So there will be different equations. So we need to apply the formulas at running as well as stationary condition. So what we have seen the definition of slip, then their formula, how to calculate slip, percentage slip, then rotor current frequency. It is simply given by slip times the stator frequency. Then similarly for rotor induced EMF, which is equal to S times E2, rotor reactance per phase, which is equal to S times X2. While running, all these parameters we can write while running. Then rotor current at stationary as well as running with respect to rotor power factor cos phi 2.